And now we move on to the last part of our discussion on optics, examples part 3. So consider the following example, example 7. You have a diffraction grating which has 1.26 times 10 to the 4 power rulings or slits that are uniformly spaced over with W is equal to 25.4 millimeters. It is illuminated by yellow light that contains two closely spaced emissions of wavelengths 589 nanometers and 589.59 nanometers. Determine the angular separation between the two lines in the first order. What is the minimum number of rulings that the grating can have and still resolve the two emission lines in the first order? So you have the number of rulings in the grating, n is equal to 1.26 times 10 to the fourth power. The the overall width of the grating is 25.4 millimeters or 0.0254 meters. You have two wavelengths that are very close together, 589 nanometers, lambda 1, and then 589.59 nanometers, lambda 2. First order, the problem tells us, in the first order, so that's m is equal to 1. We can get the slit width, the distance between two slits, a slit width, rather the slit to slit distance for our diffraction grating by dividing the total width of the grating by the number of slits. So W divided by N, we have the slit to slit distance 2.015873016 times 10 to the negative 6 meters. For a diffraction grating, d sine theta is equal to m lambda. Setting the theta, the m to 1, you have d sine theta 1 is equal to m lambda 1. We know 1, m, 1, lambda 1, 589 nanometers. We just calculated the slit-to-slit distance d. We are now able to calculate theta 1, 16.98858.065 degrees. Now, d is equal to m over d cosine theta 1 is equal to delta theta over delta lambda. So using this part of the equation, we are able to isolate delta theta. Delta theta is equal to m delta theta d cosine theta 1. We know theta 1, delta lambda. We are easily able to get delta lambda. You have lambda 1 and lambda 2. And then slit to slit distance d. The equation is complete. We are able to calculate delta theta. 3.060314575 radians. Next is what is the minimum number of rulings that the grating can have and still resolve the two emissions in the first order. So number of rulings is capital N, R is equal to N, M, where R is also equal to lambda average over delta lambda. Using this part of the equation, N is equal to lambda average over M delta lambda. So first ruling, M is equal to 1. We know we can easily get delta average, lambda average rather, and then delta lambda. We are able to calculate the number of rulings 998.8050847. So final answer, delta theta is 3.06 radians and capital N is 999 rulings. Next up, we have example number 8. You have a double slit arrangement which produces interference fringes for the sodium light which has a wavelength of 589 nanometers. This produces an angular separation of 3.5 times 10 to the negative 3 radians. If we are to replace the light with one with a with another light that has a wavelength that will produce an angular separation that is 6% larger, what is the wavelength of that light? So given lambda 589 nanometers, angular separation delta theta is 3.50 times 10 to the negative 3 radians. Let n is equal to 0 and then n is equal to 1. We can get the angular separation for these two bright fringes, the central bright fringe and then the first bright fringe. Delta theta is equal to theta 1 minus theta 2. The central bright fringe is located at the central line or at the center of the interference pattern for the double slit. So delta theta is just equal to 0. We are able to get theta 1. 3.50 times 10 to the negative 3 radians. If we now use d sine theta is equal to m lambda equation for the double slit, set theta to theta 1. That means n is equal to 1. Knowing the wavelength, 589 nanometers, we are able to calculate the slit width, slit to slit distance 1.6 times 1.68286059 times 10 to the negative 4 meters. The slit to slit distance D. The distance between the two slits of the double slit. If we now replace the sodium light with another light of a different wavelength, we'll still be using the same double slit. So that means we'll be still using this value of the slit to slit distance. But this time, the angular separation will be 6% larger. So theta now will be equal to 1.06 times theta 1, meaning theta is 6% larger than theta 1. If we now use d sine theta plus n lambda again, and this time isolate lambda, lambda is equal to d sine theta over n, replace theta by 1.06 theta 1, the equation will now be complete. We'll be able to calculate the wavelength of the new wavelength of the second light. The second light now will have a wavelength of 6.24 times 10 to the negative 7 power meters. So if we use this wavelength, the angular separation will be 6% larger. And lastly, we have example 9. Suppose the Young's experiment, which is the double slit experiment. So in some books, the two slit or double slit interference is referred to as Young's experiment. Suppose the Young's experiment is performed with blue-green light of wavelength 410 nanometers. The slits are 1.20 millimeters apart, and the screen is 5.40 meters from the slit. How far apart are the bright fringes near the center of the interference pattern? So lambda wavelength is given 410 nanometers. The slit to slit distance is given at 1.20 millimeters. And the slit this to screen distance is given by x 5.40 meters. For the locations of the bright fringes for the two slit interference, you have yn is equal to nx lambda over d. The two bright fringes that are near the center of the interference pattern are the first bright fringe, y1, and the second bright fringe, y2. By setting n is equal to 1, we are able to calculate y1. Setting n is equal to 2, we get y2. And then getting the difference y2 minus y1, we are able to calculate the delta y, the distance between the two bright fringes. 1.854 times 10 to the negative 3 meters. So that's it for our discussion of examples part 3. That's it for our discussion on the topic of optics. So thank you for watching.